So now that we know about the reciprocal lattice, let's see if we can use this to figure out what we should do to construct the Brillouin zone in more than one dimension. So just as a quick recap, if we have a block mode, then for this block mode, there should exist a certain wave vector k, such that if we look at the field at a certain position, capital R, away from an original position, with capital R being a lattice vector of our periodic structure, that we should then in this case retrieve the field at our original position h little r, but multiply it by a complex exponential minus j k r. Okay, so this is what we have for our block mode. And we also know from the discussion of the Brillouin zone in one dimension that actually there's some redundancy in the k vectors here, that you can make different choices of k vector, which will end up with exactly the same formula here. And then the Brillouin zone is the set of k vectors which is non-redundant and which you then can use to fill out the entire k space. So now the question is, how can we do something similar in more than one dimension? So pause the video and see if you can find a modification of k such that this formula here is essentially still the same and is unchanged. So this will point towards the redundancy in k space. So remember fundamentally where this redundancy comes from. If we go back to one dimension, then we have a phase vector that looks like this, exponential minus jka. And then it was not so difficult to see that if you make a modification to k as follows, if you replace k by an integer multiple of 2 pi over a plus n 2 pi over a here, that basically will result in exactly the same complex exponential here, because the a's over here cancel and then you have multiples of 2 pi. So adding 2 pi over a in the 1D case here will result in exactly the same situation. So what is the three-dimensional analog here? The three-dimensional analog, so we should have exponential minus jkr, and we should change this in such a way by adding something to k such that the whole thing is basically invariant. Now, since we know about the reciprocal lattice, what we can do is we can take the k vector and add any reciprocal lattice vector g to it. And then, basically because of the definition of the reciprocal lattice, we know that this thing here will be an integer multiple of 2 pi. So just like in the 1D case, then basically we multiply by 1, so we get exactly the same thing back. So you could say in one dimension, the size of the Brillouin zone here is 2 pi over a. In more than one dimension, the size of the Brillouin zone is given by this reciprocal lattice vector g here, at least when you only look at that particular direction here. But in any case, the conclusion is that if we have, for example, a region in k space where you have two k vectors, and it's possible to go from one k vector to the other k vector by adding this reciprocal lattice vector, then these 2 points cannot be part of the Brillouin zone at the same time, right? Because these 2 points are redundant. They will give rise to exactly the same complex exponential. So what we're looking for is this non-redundant region in k space where it's not possible to go from one point to the other point by adding a reciprocal lattice vector. So how are we going to construct this in a more systematic way? Well, first of all, let's start by focusing on the origin, and let's center our Brillouin zone around the origin. That seems like a nice symmetric thing to do. And let's also focus on one direction at a time, and let's focus on the direction given by a particular reciprocal lattice vector, and also minus that vector. So we have these 3 points over here. And then what we're going to do is we're going to look at this interval here between 0 and g. We're going to cut it in half and then have the perpendicular bisector here. And then we do the same thing on the negative interval. Now these two perpendicular bisectors, they create a region of k space. And I hope that you can convince yourself that in this region of k space, it's not possible to go from one point in this zone to another point in this zone by adding this reciprocal lattice vector G. The only 2 points where you can just about do that is if you look at 2 points here on the edges, then you can move from one to the other. These don't really count because they're on the edges. As soon as you want to move a little bit further with your starting point here, then your ending point will have moved out of this zone here. So this is basically a region of K-space with size G, if you want. Okay. So obviously, we only looked at one particular direction here, and in more than one dimension, we will have more than one directions we need to take care of. So what we will do is we will repeat that procedure for multiple directions, as many as we need, and then do the same construction with these striped zones here, and then take the intersection of all of these zones between the perpendicular bisectors or perpendicular bisecting planes. And if we take the intersection between all of these zones, we basically end up with our Brillouin zone, because what we've constructed is a region in K-space where it's not possible to move from one point to another point by adding any of the reciprocal lattice vectors that we have. So in essence, you can also say that we've created a region in K-space which is closer to the origin than to any other reciprocal lattice vector. So this sounds perhaps a little bit abstract, so let's make that more concrete by looking at a two-dimensional square lattice like this. Okay, so periodic structure. And let's introduce our lattice vectors in real space. Let's say that this is A1x, and then over here we have A1y. So this is the lattice in real space. So now, in order to construct our Brillouin zone, we first need to figure out what the reciprocal lattice is. So pause the video, go back to the formulas from one of the previous videos, and see if you can figure out how to construct the reciprocal lattice of this square lattice over here. So we had a formula to construct the primitive reciprocal lattice vectors. You might remember that we had a formula, for example, B1 is 2 pi and then times A2, A3 divided by the triple products A1, A2, A3. So these were the formulas that we've derived earlier for our primitive reciprocal lattice vectors, which will span the entire space of reciprocal lattice vectors. So in our case, remember, so for A1, we had A in the x direction. For A2, we have A in the y direction. And then we're a little bit in trouble here because this is a two-dimensional lattice. So what will we do for the third lattice vector in the z direction? So there's no periodicity in the z direction. We can sort of pretend there is one with an arbitrary period c. And then let's just hope that this c, which we've introduced in an arbitrary fashion, doesn't really play any meaningful role in the formulas that we end up using. So let's see if this is indeed what's going on. So let's plug this into our formula here. So B1 is 2 pi. And then we have A2 cross product with A3. So that's y with z. That gives us x. So we have AC unit vector in the x direction. And then we divide by A1, which is also in the x direction. And then we have, again, the numerator AC and then unit vector in the x direction. And then the good news is, as we would like to have, that c here cancels, so it doesn't play any meaningful role. So that's good. And then we can just simplify this a little bit. We have a divided by a squared, so we have 2 pi over a, and then unit vector along the x direction. It will come as no surprise that if you repeat this thing for B2, that you also get 2 pi over a, and then this times unit vector in the y direction. We don't care about the z direction because, again, there's no periodicity there. But now that we have this information, we can construct the reciprocal lattice in K-space, which, again, will be a square lattice, as our calculations have shown us, because they're on the x direction and the y direction. This time, the size of the lattice is 2 pi over a. Okay, let's say that the origin is over here, and then pause the video and try and do that construction with all the perpendicular bisectors to see what the resulting Brillouin zone will be for this particular case. I've been a little bit careless in my drawing. Let's try to make this a little bit more square, my lattice, and a little bit more periodic. Okay, it's still not great. Let's try this one more time. Okay, close enough. So let's see how far we get here. Let's just first focus on the horizontal direction. So on this point and on that point over here. So let's first look at this line. We divide this thing in half and we draw our perpendicular bisector like this. And then we repeat that for the opposite direction like so. So now we have a strip here. So this particular strip between these two lines, that takes care of the redundancy with respect to the horizontal direction over here. So now we repeat the same thing for other directions. So we look at this line, we divide it by 2, and again we bisect. And again we repeat the same thing over here, and we bisect. So now, if we take the intersection between these two strips, we end up with this square here. Okay. Just to be on the safe side, let's also take a look at these non-nearest neighbors in the corners here. What happens here if you take this direction and you bisect? Well, then it turns out that you just end up exactly at this corner over here. So you don't need to take that into account. That's already taken into account if you look at the much more stringent conditions of the horizontal and the vertical direction that we've looked at so far. So the conclusion in this case is that the Brillouin zone for our square lattice is this square region over here, and it has as side of the square 2 pi over a. So this is what our construction teaches us with respect to the Brillouin zone of this reciprocal lattice.